Okay, so what we're going to start with is what we learned last time, which is PV equals nRT. So we had talked about this, and we had done an example where we just had one set of conditions, where we just had one set of conditions, where I gave you, 3 of the conditions and asked you to solve for the other one. But that's useful for sure. But there's another part of this where what if we have a set of gas at one conditions and then we change it? What's going to happen then? If we take a balloon and we cool it down, how much is that going to change the volume by? If we take a light bulb and we turn it on and thereby heating it up, how's that going to change the pressure? Is that going to break the light bulb? If our tires go from 0 degrees to 70 degrees, something which is pretty normal in cold climates, well, what's going to happen to them? Are they going to burst? Things like that. And that's what you need to be able to do. So we can do all of this with the ideal gas law. So I've started with an example here where we have a bubble, or a balloon, we'll do the bubble next, at sea level, and it's a certain size. And then we're going to raise it up into the air so that there's less pressure, there's less atmospheric pressure, and the temperature changes, okay? So now we're changing a couple of things. We're lowering the pressure, which would do what? Increase or decrease the size of the balloon? You're lowering the atmospheric pressure, the pressure around it. Yeah. And then we're changing the temperature, we're making it colder. So what would happen there? Decrease. And we can see what's going to happen to it. Now, how do you do this? If you go through your book, I think your book walks you through this, it has a bunch of different ways of using just Boyle's law or just Charles' law or, and each one individually, and that's fine. But there's an easier way, I think, to remember how to do all of these so that you don't have to make the decision, which one am I going to use for each different situation? And to me, that's to just start with PV equals nRT. Now, what is R in that? Is it a constant? Is it a variable? It's just a constant, right? Just a number. So we could arrange this whole thing for PV equals NT, right? And set that equal to R. So for some set of conditions, whatever set of conditions that may be, that's true. All right. Excuse my computer glitches today. I am in the middle of redoing the whole thing, so it's being a little crabby. Wonderful viruses. So R2. Now, let's say we do the exact same thing for a different set of conditions. Any set of conditions, it doesn't matter, right? Just any set. And we set that equal to R, okay? Well, R is just a number, right? So if this is equal to R, and this is equal to R, what else are the two of them equal to? Each other. So let's do that. So now we have P1V1 over N1T1 equals P2V2 over N2T2. And we can do all of these ideal gas questions from this without having to make a decision about which set of equations you're going to use. So this is going to be really useful to you guys, and you're going to want to start here for most things. There's a couple of things I want to point out that we'll hit some examples with. What unit do you think pressure needs to be in here? Okay, well, what did it have to be in here? Had to be an ATM. Why? R was an ATM, right? R, the R that I gave you, it had an atmospheres in it. And so this had to be an ATM. And V had to be in liters. And then N was just moles. And T was Kelvin. And all that was kind of set up because we had the constant R in this certain unit. Now when we come down here, if we put P in as some unit, it's going to be, and we're solving for pressure, it's going to be the same unit. So for pressure and volume, and you don't really need to worry about units for pressure and volume. All the pressures and volumes are multiplied by some number in order to get a different unit, right? If you're going from atmospheres to kilopascals or back and forth, you're either multiplying or dividing by a number. So if you multiply this by that number, you're multiplying that by that number too. So this is really nice because for this, it's a ratio. You don't have to worry about your units for pressure and volume. And technically for moles, you could have number of atoms too. It's more likely you're just always going to have moles, but number of atoms would be just fine. Because again, to convert between number of atoms and number of moles, it's just multiplying or dividing by a number. So if you multiplied or divided n by one number, you would do that to the other n. Now, what about T? Do we have to convert T? Yes, because T is plus or minus, right? You're adding or subtracting, depending on what way you're converting, you're adding or subtracting 273. So because of that plus or minus issue when you're converting between Celsius and Kelvin, you always have to put temperature in Kelvin, okay? You can't leave temperature in Celsius. So pressure, volume, and moles, we don't have to be too picky about units when you're using this form. When you're using this form, do you have to watch them? Yeah. Now sure, you can always just convert to atmospheres, liters, and moles and be safe. That's fine, and if that's what you want to do, that's okay. But it'll save you some time on exams and just homework in general. If you know when you're doing this and you have 765 millimeters of mercury, you can leave it like that. If you have 2 milliliters, you can leave it like that. But if you have 60 degrees Celsius, can you leave it like that? No. So if your temperature is in Celsius, what are you going to do? So on the exam, when I give you a temperature in Celsius, you're going to convert to Kelvin. Okay. All right. So let's actually go through and do this example. So I've walked through a little bit of it, and we'll do it on the screen as well. But it's useful sometimes to make a table like this. And so I wanted to show it to you kind of done out without necessarily having to write it all out. When you get these where you are changing multiple things, it's a lot of times a lot easier to just go ahead and write a little table out, making sure that when you go to fill everything in, you're fine. Notice when I fill my temperatures in here, I just write in the plus 273. Don't write down 60 and 70 if you make a little table like this. You'll fill it in wrong. So just write in the plus 273 or actually solve it for that number. Okay. But as usual, I prefer to do this over here, so we're going to switch over here. Okay, so we have our balloon. We are letting it, we blow it up at sea level and then we let it rise, and we want to know what the new volume is. So we start by just writing out this. Now we decide what isn't changing. So is our temperature changing? Yes. Is our pressure changing? Yes. It's sea level at 1 or higher up at 0.4. Is our volume changing? Yeah, that's the thing we don't know. That's the thing we're solving for. So what's the only thing here that isn't changing? Moles. So just cross it out. It's the same on both sides, so it doesn't matter what it is. If it's 3 over here, it's 3 over here, so they cancel out. So that leaves us with like that. And so that's where we can start from. So that's sort of your yeah.
Could you explain a situation in which the moles would actually change, not explicitly stated?
It would have to be explicitly stated. It would have to be something like, and then you added another gas or something like that. We get into that a little bit more when we start doing Dalton's law of partial pressures and things like that, where we're adding in different gases together. But they'd have to say something. They'd have to say, you know, I think the next example we're going to do has like a bubble rising to the surface, and we're assuming that the moles doesn't change, but they could say, you know, half of the moles of gas was lost to the water, something like that. They'd have to tell you. Okay. So we're left with this. Now this is where the little table that I had up in that line would come in handy to go through and actually write everything down. You don't have to, but sometimes it's helpful. I'm just going to go ahead and fill in. So our P1 is 1 atmosphere. Our V1 is 0.55 liters. And then our temperature is 70 plus 273. Now we do the same thing for this. So our P2 is 0.4. We don't know what V2 is, so we're just going to leave it. Then we write in our T2, and I just add a little Kelvin there so we remember that we switched it. And we solve all of that for V2. Now, there's a couple of different ways of thinking about this, so I'm just going to draw a little line here. I filled in the numbers first here, mostly because I think that's how people prefer to do it. People, in general, you guys tend to prefer to fill in the numbers first. Personally, I don't think that's the best way to do it. I think the best way to do it is to rearrange your variables first and to actually solve this first. And so in that case, you would have V2 is equal to P1 V1 over T1. The T2 comes up, and the P2 comes down. Okay, so either way, you end up getting 1.33. But it's just, do it whatever way makes the least number of mistakes for you, but give it a shot both ways. On your homework, give it a shot both ways and see which way you like. See which way you make the most mistakes. I think getting used to moving around your variables is probably the most useful way, but I'm not gonna mandate that or anything. You can always do it this way. So either way you do it's fine. Just know that both are available, and this will probably have you make less mistakes, but I don't wanna promise that. Okay. So the next slide is just a whole bunch of examples, so we're just going to stay here. Okay, so now we have a light bulb example. So this would be useful to see how strong your glass has to be in a light bulb to know whether or not it's going to break. Because a light bulb isn't just a filament, right? It also has some sort of gas around it. The way that a light bulb works is that it has to be able to heat up and glow without actually combusting. And so if you have oxygen in there, it combusts. So you have to put what we call an inert environment, an environment that isn't going to interact, isn't going to react at all. So argon does that. So your light bulbs, and I think this is talking about incandescent light bulbs, not the fluorescent ones. But so in order to do this, you need to have argon. And they tell you the pressure and temperature that they start out with. Of course, what happens when you turn a light bulb on? It gets hot, especially the incandescent ones. And so you need to go through the same sort of process. And again, you can just start from here, kind of write this down without even having to give too much thought as to what you're doing to start off with. And now you say, okay, what isn't changing? So what in this situation is staying the same? Volume, right? It's a light bulb. The glass isn't going to stretch out or shrink. What else? Yeah, moles, right? There's not going to be argon escaping or coming in. So we can cross those out. And so you get that. Now, I had a question right before class, which I think is actually kind of a good thing to bring up, that this got talked about in reverse in one of the discussions, where it was T1 over P1 and T2 over P2. Is that a problem? No, these are ratios, right? So you could flip-flop them. You think about your algebra classes and cross-multiplying, right? The T2 comes up here and the T1 comes up here. The P2 would go down here and the P1 would go down there. So these could be inverted. You could write this as T1 P1 equals T2 over, T1 over P1 equals T2 over P2, and that's fine. I think it probably got done like that in your discussion because it made the math a little bit easier. Sometimes if what you're solving for is in the denominator, it is actually a little bit easier to flip it. That by no means is mandatory, but it is useful to know and remember that that's how ratios work. Okay, so now we can go ahead and we can fill everything in. I'm going to go ahead and solve for P2 first. And as I talked about before, you're welcome to go ahead and fill in numbers first if you prefer. The other nice thing about rearranging your variables first is you can check for sig figs at the end without having to check for them at each point, and it's a little bit easier there. And so we fill everything in, and we solve. So we would know that whatever glass or whatever system we use to contain our light bulb would need to be able to stand up to 1.48 atmospheres, which, shouldn't be too big of a deal for it. Okay. Questions? No? All right, so now we have a bubble. Oh, yeah. Say that a little louder. Oh yeah, let's check for sig figs. So let's see, yeah. Sometimes, toward the end of class, I start forgetting that. Let's go through and do the sig figs part real fast. So for this, we have 85 and 18. Now it's addition, and so it's going to be to the ones place, right? So it would actually end up being 3, because it would be whatever 273 plus 85 is, but you're holding it out to the ones place. Let me write it down real fast, but I'm going to plug that one into a calculator real fast. So 358. So it's 358, and because it's addition, this is a good remembering on addition actually, because a lot of times we forget about sig figs with addition. Because it's addition, we hold out to whatever the lowest number of places is, which in this case is going to be your ones place. And so this gets taken all the way out to your ones place. And the same thing will happen here, where this gets taken all the way out to your ones place. So because of that, this, and this will all end up with 3 sig figs. Does that make sense? Everyone got that? Let me say it one more time, because I know addition sig figs get forgotten about. So here and here, this to this, it's addition. So we go out to the place, not the significant figure, right? So we use significant figures when we do multiplication and division. We do places when we're doing addition or subtraction. So the lowest number of places here is that you have the tens in the ones place. So you have this. And so they both go to the ones place. So you can add it to the ones place, and so you end up with 3. Okay? If this was 80 and 273, then you would only go to the tens place. Yeah? You technically have to do it stepwise. So when you go through and you do sig figs, every step is each on its own. When you rearrange it like this, if it's all multiplication and division, okay, you just go lowest number of sig figs. If it's all addition or subtraction, you just go lowest number of places. But when it's both, then you have to look at it a little bit closer. So we start here and we say, okay, that's 358. And then we would go to the next one and we would say, well, that's 291. And then what we're doing is we're taking this, multiplying by that, and dividing by that. So it's 3 sig figs times 3 sig figs divided by 3 sig figs. And so it's 3 sig figs. Okay? Good refresher, especially for when you guys go to labs. Because, you might lose like 2 or 3 points on an exam for sig figs, but in your lab classes where it's really important to know sig figs, you'll lose a lot of points. So good refresher on that. Don't groan, lab is fun. You get to play with things. Okay, so now the bubble. So now we have a bubble, and this is kind of like our balloon one, except now we're going from the bottom of the ocean up, or the bottom of a lake, I suppose, all the way up to the top. So we have our temperature changing, our pressure changing, temperature here, pressure here, and we want to know our new volume. So it's very much like the balloon problem. So again, we write everything out. We start from here. This is sort of, whenever you see these ones where you have 2 different conditions, this is your first step. Just write this down. Then comes the, thinking step. What here isn't changing? The moles. Okay, so that leaves us with P1, V1, and T1, and that's it. So, and of course P2, V2, and T2. So now we solve for what we're trying to solve for. So what are we trying to solve for? V2. So we're solving for this. So we want to get that on its own. Move a little bit faster with this one. So for a more step-by-step look back at the balloon one. We're solving for V2. So we have P1, V1 over T1. The T2 gets multiplied up. The P2 gets divided down. And so you have this. Now you fill in all your numbers. Now, I'm going to fill it in like this. Is that okay? I hear a variety of answers. Let's go ahead and write everything down, and then we'll look and we'll see what we think. Okay, so let's look at our units here. Hang on, I copied something down wrong. Spoiler alert. There you go. Okay, so let's look at all our units. We have atmospheres here and atmospheres here. So those would kind of cancel out in our head when we get our final answer, right? And we have Kelvin here and Kelvin here. And so those are going to cancel out. What would that leave us with for V2? Mils. Is that an okay volume unit to have? Yeah. So we'd have 14 mils. Okay? Now, we can't do that with Kelvin. Because again, with the Kelvin, we have this issue of addition. In addition and subtraction, you'd have to remember, again, thinking back to your Algebra 2 days or Algebra 1 days, if we had, something plus 273 here, that would have to be like factored in, right? And then factored in here and factored in here to work that algebra. You can't just divide it straight down like that. And so Kelvin, you always have to go ahead and convert. But something like atmospheres or pascals or millimeters of mercury or torr or any of those units, all of those are just multiplying and dividing by some number. So you can leave them because they would cancel here. Now, what if I gave you this unit in pascals and I gave you this unit in atmospheres? Could you leave those? No. What do you have to convert to? The same thing, right? It doesn't matter which one you convert to or if you convert to something else entirely, but they have to be the same. So, and that's a little bit easier to see when we have it kind of written out like this. Whatever pressure is in, pressure has to be in. Whatever volume is in this case is what you're going to find. If we had both volumes, they'd have to be the same. So whatever unit you fill in for pressure, it's got to be the same, whichever they are. Whatever unit you fill in for volume, it's got to be the same. And if you're solving for one of those, it's going to come out to be the same thing you put in. We put in milliliters, and so that's what we get. We had both of these be atmospheres. Yes? Oh, you mean the conversions? Yeah. It should be on there already. It should be on the, I've kept the same equation sheet the whole way through. It should all be on there in the one table. If not, I'll now double check it and make sure. Okay. One last one to do on this slide. Octane, and I give you the formula, is in gasoline. When combusted, it produces carbon dioxide and water. So what group of study material is back to haunt you here? Fundamentals. If you get to like the book problems and sapling problems and you're like, wait, this limiting reagent thing, I think I remember it, where do I go for help? That's all in your fundamentals section. So when you hit, balancing equations, limiting reagents, mole to mole stoichiometry, things like this, the chapter 4 is saying, well, we taught you that in fundamentals, or at least we reviewed it in fundamentals and it was taught to you in 1P or high school or wherever. Go look there. So when you get stuck on those problems, make sure you know where to go for help, and that's where you want to head. Okay, so continuing on with this though, we have to write out the equation. So we can write out C8, H18 plus O2 goes to CO2 plus H2O. And now do we just go ahead and start converting things and doing our pressure calculations? No, what do we have to do? Balance it, good. So, this is always sort of a guess and check sort of thing. Probably if I looked at this right away, I'd say, well, let's put in 8 here and see if it works. And if we do that, we would have our 16 oxygens here. We know that there's no way that we can get an even number of oxygens. Well, actually, hang on. So let's go ahead and put like a 9 here, right? Because we balanced our 16, or 8 carbons. We've balanced our 18 hydrogens. And then at that point, you're gonna look and try to figure out a way to make this work. And this is an odd number, right? So it doesn't work. So when you get stuck like that in a combustion problem, what do? You double everything. So this becomes 16. And this becomes 18. I'm going to rewrite this too because it's a little messy at this point. So that's the thought process, right? Kind of a remembering on how to go through these. You just start looking at what you can balance and go from there. You'd look at the carbon first and you'd say probably an 8. That I think would be your first guess. And then you'd look here and you'd say probably a 9. That would be your first guess. But then you say there's no way to get this to work, so I have to double it. Okay, at that point, now you just have to worry about your oxygens. And so you do whatever you need to do to the O2 to balance that. Okay? So kind of re-going through the thought process on combustion reactions. Okay, so now that we have this, we can figure out what's happening up here. So we know that we have this, and this, and this. We have 1 gram of octane. And we want to know if we have 1 gram of octane, what volume of oxygen do we put in? So we're going to have to do some stoichiometry here. We're going to have to start with 1 gram of octane. And we're going to have to get to something of oxygen. What's probably a good thing to get to of oxygen? Moles. So can we just do grams to moles instantly? We've got to go through the moles of octane. And where do you get this number from? Periodic table. Now we have to go from moles of octane to moles of oxygen. And where do we get those numbers from? The coefficients, right? You're getting them from here and here. That's why we needed a balanced equation. Now I want volume, so I'll just plug in 22.4. Does anyone have a problem with that? That's how you did it in the fundamentals. So can I just plug in 22.4 liters per mole here? I'll give you a hint. Would it be in this chapter if that was all there was to it? No. What is that 22.4 liters per mole? What does that refer to? It refers to a very special set of conditions. STP, right? So back when we did this sort of thing in the fundamentals chapter, that was really all we knew how to do. That was all we cared about. So every time that we gave you a problem like this, we said add STP. And then you're like, okay, it's STP, I'll just do what they tell me to. Now we can do things that aren't at STP because we have the ideal gas law. So we have PV equals nRT. So we can go through and we can solve this for moles. Now we have moles, we have pressure, and we have temperature. So can we find volume? Yeah. We can use this and we can solve for it. So we plug in everything. Now, in this case, I gave it to you in atmospheres, but if I had given it to you in pascals, would you have to change it? Yes. Why? Because of R. And of course, we have to always change our temperature. So we fill all of that in, and we get our answer. And double check our sig figs real quick. Can we see we have 3? So we're all set. Okay. Any questions on that? Yeah, way in the back.
I was just wondering if it being so bad if we just use the different R with the units.
Okay, so that is a good question. The problem with that is then you would need a whole nother, you'd have to list R for like every possible unit. So you'd have to list R for millimeters of mercury, torr, atmospheres, pascals, kilopascals, and that would get a little tedious. So because it's easier in this case to just convert whatever is given into the right unit, that's the method you want to go with. And what I'll give you are, and I'll give it to you in 2 different units. The one that I have up here, the 0.0821 liters atmospheres per Kelvin mole, and I'll give you the energy version of it. And those are really the only 2 versions of R that we use. But good question. Theoretically you could, it just comes down to which one's more work. And it's more work to list out all of the versions of R than it is to just convert when needed. Okay. Now, moving on with this sort of examples and things of that sort. Maybe. Okay, density calculations. So, again, if you kind of forgot what density means and all of that, go revisit the fundamentals on it. But real quick review here. So remember that density is equal to mass divided by volume. So you'll see it in units of mgs per mil a lot of times, or any sort of mass unit or over any sort of volume unit. Molar density. Now that's something that we don't talk about a lot, but it's going to be really useful here. So if density, just as we call it density, is grams per volume, we can kind of see how molar density is going to be moles per volume. And we can see how that would be a useful unit, right? We don't always want to have to deal with grams. Grams isn't the most convenient unit in the world to be calculating things with, right? It's convenient in the lab because you can measure it. It's nice to be able to scoop out a sample on a plate and be able to weigh it. But it's not very convenient for doing calculations. We always have to convert to moles, which luckily for us is not that big of a deal. It's just multiplying or dividing by something. And so we can still use grams all the time. But now we want to be able to use this molar density too. Because what would be our unit here? Moles over liters. Can we get moles over liters using our ideal gas law? Well, sure. We have PV equals nRT. We have moles and we have volume. So if we want to get a molar volume, whenever we want or molar density, we could just solve for N over V. And we can end up with P over RT. And so this gives us another unit that's sometimes useful to work in and useful to solve things for. Okay? Now, molar mass calculation. So one of the things that we've kind of done off and on throughout this course is solving for a molar mass in different ways. I give you, the empirical formula and some other data and you solve for the molar mass. Or I give you the molar mass and the empirical formula and you solve for the molecular mass. Or excuse me, the molecular formula. Things like that. So we're going to do some examples where we need to be able to convert between these 3 things. Molar mass, density, and molar density. Because now the useful thing here is think about what you would do in lab based in what you would want. So can we measure the density of a substance? Grams per liter. Yeah, right? I mean, if theoretically you could build some sort of setup with the scale around it, and you could see how much a gas weighs. I think the really rudimentary version of this is you take a balloon and you tear the scale with a balloon on it, empty, and then you can blow air in and you can see how much the air weighs. But you could do this with pure gases in a more, elegant system too. Can we measure the density of a substance? Sure. We can go through and we can measure that. So now we can find the difference, and we can find the molar mass. We can find the molar mass simply by measuring these two things. We can measure the density, and we can measure the molar density, and we can figure this out. The molar density is a little bit harder to think about how you would measure it, but you can do it. Now, you can do this a few different ways, and this is why I have these two slides. You can do this by remembering these equations and manipulating these equations to get what you need. Or you can do it by looking at the units, which is why I put the units up here again. Looking at the grams per mole, grams per liter, and moles per liter, and just seeing what you need to move around and what you need to change around to get the right number, or to get the units correctly. Whichever way you want to do it is fine. Different books, different websites, different people will show it all different ways. Okay, best way to explain this is by doing an example. All right, this is a little bit of a long example, so you may want to have an extra sheet of paper around to add on to it. So we have phosgene. I just give you the name. This obviously isn't a name that you would have to know, to put down. It's a colloquial term for it. It's a highly toxic gas made up of carbon, oxygen, and chlorine. So we know that it's going to be some form of COCl with, something down here. Now, I tell you the density at this. What is the molar mass of phosgene? Okay? So let's think about this. If we have pressure and temperature, and we know the molar density, what else can we solve for? Well, we know the density. So let's go ahead and rearrange this like how I had it on the slide. We'll rearrange it for N over V. And we'll see what we can fill in here, okay? We know the density, we know the grams per liter. This will give us, what is it called again? It's moles over liters, so it's molar density. So then we'll have the density, and we'll have the molar density. And what I told you on this slide, and you're believing me for the moment, is if you have two of those things, you can solve for the other one. And the other one was molecular mass. So we were given the density, we're finding the molar density, because we can measure all this experimentally. And now we're going to solve for then we're going to solve for the molar mass. Okay, so step one then, solve for the molar density. So we fill everything in exactly as we've been doing, being careful to watch our units because there's an R. Whenever there's an R, we have to watch the units. Sorry, the units for R tend to get a little squished, but. And we're at 298 Kelvin. So we solve this and write down our number. Okay. So now we have this that was given. We have grams per liter. And we have this that we found, moles per liter. Now, what is the unit for molecular mass? Because that's what we're trying to find. We need molecular mass to be able to find the molecular formula, right? So if we need the molecular mass, we need to know the units. Molecular mass, right? How many grams are in 1 mole? So the molecular mass unit is grams per mole. So this is what we need. We need to get grams per mole. That's our goal. Okay, so we have these two things that we know are true. this grams per liter and this moles per liter. What can we want grams on top, right? So we need to play around with units to make this work. So, well, I want grams on top, so I'm going to put the 4.24 on top right away before I really have to do too much thinking about it. Okay? Now I want moles on the bottom. Well, what do I have with moles in it? This. And you say, well, but there's liters there. You can't have the liters in there for molar mass. Molar mass doesn't have a liters unit in it. But look what happens when you do this. What happens to the liters? They cancel out. And that's what you'll find with any of these three things that I talked about on that slide, is you can use those three and you can move interchangeably between them by playing around with the units. And so when we get this, we end up with that. Okay? So that's our molar mass. So now we know that we have that because we're going to need it, right? Every time you want to solve for a molecular formula, you're going to need a molar mass. Okay, now we're back to all of those problems you loved so much and are missing from the fundamentals section. So I know that you were really missing them, so I wanted to make sure you got to see them again. So we have this much carbon, this much oxygen, that much Cl. Now, how do we go about solving for this? This is where there's a couple of different ways. In the beginning, a lot of times you just solved for, you had to assume that there was a 100-gram sample. You can do that, and that's fine. If you do it though, there's a couple of other things that come into play. There's an easier way to do it in this case, and that's to know that your molecular mass is 98.9. So then if I want to know how much of that's carbon, what do I have to do? Multiply by the percent. So that's the easiest way to do this. There are other ways, but that is by far the easiest. So we're going to take each one of these and we're going to multiply by the percent. And again, if you wanted to do the 100-gram sample thing, that would work too. Now, that gives us our grams, right? Do we want grams when we're trying to figure out a molecular formula? No, what do we want? Moles. So we have to take each of these and convert to moles. Actually, let me add a little more to that. Okay, so now we can go through and we can calculate all those numbers out, and we get 112. Oh yeah, sorry. Okay, so what does that mean our molecular formula is? COCl2. Now, if you had gone through the 100-gram sample version of this, all you would have ended up with, what would you have ended up with at the end? You would have ended up with an empirical formula, right? And then you would have had to look at the empirical mass and the molecular mass and compare them. So you could do it that way, it's fine. I just think this way is a little bit easier. Or at least faster. I suppose easier is subjective. Okay. All right, so starting off a little bit with this, Dalton's law of partial pressures. This is going to come into play with mixtures where you have multiple types of gases coming together. So what's going to happen here is that you can treat each gas completely individually, which is really nice. You can treat it as if you have one gas there and another gas. If you have two gases mixed in a container, you can treat it like you have one gas in that container and do all the calculations for that. and then you can treat it like only the other gas is in the container and do all the calculations for that, and then you just add them together, which is really handy. So this is saying this a little bit more formally. Total pressure of the mixture of gases is the sum of the individual. So if you have a total pressure of 2 and you have 1 mole, or you have equal numbers of gas, that means that you have 1 mole of one gas, or excuse me, 1 atm of one gas and 1 atm of another gas. Your total pressure would be 2. That means if you have 2 atmospheres of one gas and 2 atmospheres of another gas, your total pressure would be 2 plus 2 is 4. So that's all this is going to say. This isn't written out in really formalness. Okay, so this is exactly what I said, just written out in terms of equations. So, it's useful equations, which is why I want to go over it. So pressure A, pressure B, pressure C. That's just saying one gas plus another gas plus another gas. All of their pressures, if you add them up, they equal the total. So that's exactly what I was saying before. If you have 1 atmosphere of a gas, 1 atmosphere of another gas, 1 atmosphere of another gas, and 1 atmosphere of a fourth gas, how many atmospheres total do you have? 4. You just add them up. Now, what is pressure equal to? Well, think about your ideal gas law. You have PV equals nRT. So pressure is equal to moles times R times T over volume, right? If we solve that out. So all this is saying is that, well, you could take and you could solve for pressure, you could solve for pressure, you could solve for pressure. And you can add them all up. You could also do it separately. You could do it in 3 completely separate equations in 3 different parts of your paper, and then add them all up at the end. But if you know the moles of all your gas, and you know the temperature and the volume, which if you think about it, you can generally measure your temperature and your volume. And if they're in a container, what's going to be true about the temperature and the volume for each gas? It's going to be the same, right? It's not like the gases are going to sequester themselves and say, I get this corner, you take that corner. Gases don't do that. So the gas is going to be spread throughout the whole container, so they're all going to have the same volume. They're all going to have the same temperature because you can't have 2 different gases mixed together at any sort of equilibrium and have the one gas say, well, I'm going to be cooler than you. That doesn't work either. That wasn't meant to be a pun, sorry. So then you have RT over V. So all this did is it factored it out, right? It took the R, T, and V and said, well, R is a constant. In this case, T and V aren't going to be different from the 2 different gases, and it separated them out. And it said, okay, so now if you want to know the total pressure, you add up all your moles, and you can do this, and you just multiply by RT over V. So you can use the ideal gas law, the PV equals nRT, and just use your total moles. You add up all your moles of all your gases, fill it in for R, and you can use the ideal gas law just like you did before. And we'll do some examples of that next time.